Now I want to go on another topic, which came up also earlier on, which is name resolution. This is very important, actually, and because it really helps you control understanding what's happening in your code, I think. So before we enter the words of templates and context expert, it's better to have a refresh at least on what name resolution is in C++. Sorry. So, what is name resolution? So in your program, you write variables and call functions. They are defined by you, right? You programmer or somebody else define the symbols. And when you use the symbols, the compiler has to find out what they mean. Right? You use a variable x, what is x? Well, you actually use the symbol x, what is x? Right? If you just use the symbol, it doesn't even mean that it is a variable or a function or a class name. So what is it? So there are a few rules that apply. This is called the overload resolution rules. The first thing that happens is called argument-dependent lookup, ADL. Then the employee template argument deduction. We will see more when we go into the templates. It will look for that symbol over there, right? You search for the symbol that matches. If there are multiple symbols that match that symbol, it will go through overload resolution. It means there are many options. I need to pick up the right one or the best one. And there are rules for specifying how this happens. If everything fails, so either there's no such a symbol, or there are more than one symbol with the same that the compiler cannot decide for which one it has to pick, then you get compile error. Either you cannot find the matching candidate, or there is this symbol is ambiguous. I don't know which one to pick. So when is a name resolution coming from? There are two types of name resolution. There is an unqualified and qualified name resolution. And this pops up in error messages. So in error messages, you will see unqualified resolution for this symbol and say, what does that mean? So unqualified lookup is for name that are just names. I get X, foo, as a look for X, looks for foo. This is unqualified. The qualified are the one that happens after the column operator, this column symbol here. When it happens after that, that is called qualified, because now I'm telling the compiler something specific. And the thing on the left of this operator is looked over certain classes of types. It will go through namespaces, class types, enumerators, and templates. Class templates. So if I have a column n, I know what n is something inside A. Then I go to A is a class, and there's a static member n, so I can access and I can assign n to 42. This is qualified. If I'm doing int A and A equal 10, this is totally valid. When the compiler sees A equal 10, it goes to A and say, what is A? It goes on the scope, and the first thing it finds is an integer variable, which is A, right? It goes and finds this one. This is an integer. I assign 10 to A. So this code works up to this point. This is perfectly legitimate code. The last one, this becomes unqualified search for this guy, And this becomes problematic because now the compiler goes into the scope and say, what is A? A is a variable of integer. A, B doesn't mean anything. You get a compilation error. Which the error is expected semicolon before B, which is one of the most annoying errors you can possibly have because you have no idea why that happens, and you have to look up and say, okay, this is just because I have an integer, because I have a variable with the same name of a class, and the compiler got confused. Clear? So we have qualified lookup when it is on the left of the symbol, unqualified when there is no such a symbol, and the compiler can get confused because unqualified lookup means something else than colon colon. When it's colon colon, it goes to namespaces and classes and look over among those guys what matches.
One question. So, but that code won't compile, right?
This code won't compile, yeah. You get an error at the lines over there, here, right? Shouldn't compile. If it does, I quit. I go home. Oh, it depends on what compiler you're actually using, though. This was, I don't remember what compiler I used, but it might be the Clang gives you some other kind of error messages. Clang is usually better in giving you errors that makes more sense. So ADL, argument dependent lookup. So do you know why this works? Cout is a global variable, yes. I love this example. What is this one? It's an operator. And operators can be overloaded. So this is actually just a function call. The function call looks like this. Operator, less, first argument std cout, the variable, the global variable, and hello, this constant string. Now this becomes an unqualified lookup because there's no column, and say, where is this operator defined? And actually, there's not one operator defined, because there is one defined, but it's inside the namespace std. So what happens, ADL, argument dependent lookup, looks at std cout and says, well, cout lives in std namespace. Let me look in a namespace std if this guy is defined.
So I have a small refinement. So compiler looks not at std cout, but at std o stream, because well,
yeah, on the type, yeah, it is
yes,
it is cout. So you can do cout, and then cout is a type that lives in std namespace. Yes.
And it will look for all the arguments. Like, let's say we did not find it in the std namespace, it will abstract for the.
Yes, if you put here some other class, and you have this operator defined in your namespace, whatever, this will become a compiler error, because the compiler cannot choose between std namespace and your namespace. So there are cases in which this doesn't work. But usually you shouldn't define your own operator less inside your namespace unless you really know what you're doing. Like for instance, in this case, if I know I'm not going to use it for doing output. Why is this not working? Yeah, you need to do end L is not so the compiler looks for end L and it doesn't find it anywhere because it is inside std namespace. So it will simply say I don't know what the end L is. So ADL looks just for the function names, not for the arguments. So it's not because the first argument is the namespace std that also end L will go and look into std. So suppose that we want to do clever things. I want to overload std algorithms with my algorithms. So when the users say for each, I want to intercept and work with my stuff and not with their stuff. So I want to have a for each something that actually calls std for each. But I want that this for each will go to vector begin to vector end and apply certain function. This is a lambda. Then this will not go into this for each because argument dependent lookup again, because v is in std vector of integer. So this will not call this function here. It will go first for the ADL, right? But if I want to call my version, I need to explicitly say column for each, which basically says qualified name lookup for each. On the left of the dot, there is nothing. That is the root. It's like a file system, if you want. It's just the root. And it goes to the global namespace and find for each in this case. And this becomes a qualified lookup for each. I guess we will see a lot of ADL with Anton.
Yeah. It's not just the file scope, it's really like the global namespace.
The global namespace. Yeah. Well, it will go also here, right? In this includes files. So if you include files, it will be inlined there. So everything will be visible in this translation unit. ADL can be used for good. It can be your friend, and I guess Anton will expand on this quite a bit. But basically, look at the code around here. We have a class A defined namespace X and a class A defined namespace Y. So I have a namespace X and there's a class, a namespace Y with another class, with the same A class. And also a function foo that takes A, and then it's I'm X or I'm Y. Then in my main, I can call, basically, this function foo, and depending on the type that I'm passing, bar XA will call foo X, but foo X will go to the right version. This might take a few seconds.
Sorry?
Yeah.
Just one short question. Is it that you showed something similar before and you said you were going to clear it up later? Is it like, I still don't get why you call a template function without a template argument? Like,
yeah, so, okay,
just the gist of it.
I anticipate here is the fact that when you get the compiler takes XA, for instance here, check the type, and see that there is a function here that is a template function with type T. So it will deduce the type of X and substitute the type T here. So you don't have to explicitly mention the template argument. It will be deduced for you. Yeah, we will see plenty. So, yeah, you're right, though. I keep saying we will see this one and never get to the point. Okay, so now we have the same syntax here that does two different things, right? In one case, it will print I'm X, and the other one, it will print I'm Y. What is this? It's basically polymorphism, right, without virtual function calls.
One important point that but you can place first the definition of bar and only then definitions of foo, and it will still work.
Yeah.
And this means that you can define the generic behavior, how bar is defined in terms of foo, before even before the definitions of foo. So this means that this allows you to write the generic code, basically.
Yeah, so you don't need to have all the stuff before doing.
Yes. So
before doing it, right? You can say some sense.
Yes.
Customize later, or do you do?
Yes, but you can easily ruin this behavior if you, in the definition of bar, if you will add, if you qualify foo.
Oh yeah,
example,
if you qualify with the
with
namespace, yeah.
Then a compiler will complain, or if you
for one of the two cases.
Yeah, yes.
So now we decided we go to ADL, we do the template resolution. We will see more later what that is. And now we are ready to get overload resolution. Now we have a certain number of samples, certain number of names that can be valid for us, and we need to decide which one is the one that we want to take. So now we need to determine which one we call. We have several options. They're not all the same. Some are better than others. And so what is the rule? Well, we select the best one. Sounds a little bit sloppy as a definition, but it's actually a good definition. It's the most specialized. So for instance, if I have three functions here, right? Function 1, 2, and 3. Foo takes int and int. This one returns a double and takes a float and an integer. And this one returns a char, something of type t and integer. They're all foo, so when the compiler looks for foo, and go and list all these guys will come up in the list. So when I call foo of 3 and 4, which version do you think will be called? Yeah, the one?
Right? You're missing you have one that returns a mean, one returns a double, one that returns a char, and that one's capturing nothing.
Yeah, but return values do not interfere with overload resolution. It's only the arguments. So the fact that I'm not assigning anything here is perfectly valid. The rules still apply. So since the 3 and 4 are ints by definition, I call the first version. The second one, I could call the second one too, right? The 4 will be passed as an integer, and 3 can be converted to a float, and is completely legitimate. So if I didn't have the first version, the second one might have been a good candidate, right? It's only that the first one is perfect. I don't need to do anything. I just can call it. If I do 3 and 4.3, what happens? Who said one first? Who said the second one? Now it's the first one again. Reason is, the first argument is 3, doesn't need to do anything. The second one is a double, and you need to convert this anyway in any of those. So instead of doing conversion to float or type deduction here, you just have the integer, and you convert the second argument to a double, to an int. And you go to the first one. But if I do it here, foo3.4 and 4, which one?
You should have a warning, no implicit conversion when using the second one.
But you're not using the second one.
No, I mean
Yeah.
the second example. So, when using the first one, the compiler will return a warning.
I don't. No, I think this is an implicit conversion. I don't know. We can check. It's a good question. Where is it? Oh, here it is. So int foo int goodness. Okay, now foo 3.4. In comma and comma. No return statement. Yeah. So no, doesn't complain. Yeah.
Why does it prefer to convert the float to int and not the opposite in your example in the slide?
Haha, great. Because 4.3 is not a float, it's a double. 4.3 is a double by default. So it will have to convert anyway to int or to float. So there's no, every time the compiler has to change type, it doesn't see a type which is better than the other. Actually, this is this case here, right? This case here.
But you're choosing the first option.
Yeah, here, for case B.
Yeah, by converting the first one to float and the second one to int.
No, it goes to 1. The first goes to int straight, and the double is converted to int. In this case, I will have to convert the first one to float and the second one to int. So this is actually the case where I thought you were talking to. If I say 3.4 and 4, now 3.4 is a double, it's not a float, so it will have to convert this into float anyway, right? And for the compiler, it's not that the double and the float are similar. Yeah, let's pretend they're the same. No, it's a type conversion. It would not do it for you. So instead of converting this to integer or this 3.4 to float, which are two conversions, it will just choose to pass it here where there's no conversion at all. It would just become a double. So here you go to the template version. In this case, though, now 3.4 is a float, and now you go to the second implementation. The second one is picked. Why the second one is not the third one? Because here it's true that the float can go straight to t. But here you have already the thing, so you don't have to substitute the type. It's already ready for you, so it's the function you should call.
And it is not ambiguous.
It's not ambiguous at all. Yeah. So even though if you put the float here, you get the same function, let's say function, the same signature, the other one, it doesn't have to do anything to get it working, so it will pick up that one. What happens for this case? Which version? let's look. The first one will imply converting the doubles to integers, so two conversions. This one will imply two conversions, one to float and the other one to int, two conversions. The third one will imply one goes through double and the other one is converted to int. So it's simpler. It's just only one type conversion instead of two, so it goes to the templates version. Here, 2. Yeah, 2. The first one is double, is float. It will pass it through here. The second one will be converted. The second one will be converted here too, but then you have, in addition, to do the template substitution. And here you have to convert the first argument. Here you don't, so the second one. But what if we remove the second one? We remove the third one. So we remove the template one. What happens? We see the template is called here and here in two cases. Let's ask the same question. Which one will call here? Well, we've seen already is just the same as before, right? Removing the specialization doesn't change anything. We're already being picked up the other one. This one would also be okay, because it already before it was going into the first one. But what about this one? The second one? Why? It has to do a conversion anyway. From double to float is still a conversion, so this is error. This is ambiguous because now it doesn't know if to convert this to an int or to convert this to a float. It can call both functions, right? They're both valid. It just doesn't know which one to pick. It doesn't know what we want the compiler to do. And this is why it just gives an error. It's ambiguous overload. This one will go on 2, of course. This one, same thing. We just give an error again. He has to convert all the types. And this one is funny. This one, he has to convert. The first one doesn't have to be converted. The second one will be converted. Here it can convert the first one and also the second one. So it'll say the first one goes straight. So the second one is the version that is picked up. It has to do only one conversion instead of two. What it teaches here is that the fact there's no preferred conversions. It's not something is similar to something else that prefer that or the other. If there is a type conversion, the compiler will consider them all at the same level. And this is a very sane thing to do, because otherwise you end up in having to think twice of what you are doing. And you already have enough to think when you program C++ without going into these details. What have we done here? Okay, now we have, we translate, we just changed the int and float. Right, so before it was float and int, and now is an int and a float. And we asked again, in this case, what happens? Again, you need to convert both of them. So you need to convert the double in the float and integer, so you have an error again, because it has to convert both. In this case, you go to the first one, because the 4 doesn't have to be converted. But then when I do this again to first, there is one which is interesting somewhere. And here, again, what happens, this is still an error, because you have to convert both values. And in this case, the second one. Right, so I think we understood a little bit the rules. So here now, let's see what's up here. Okay. Now let's go back. So here now we have the int and float. So we have swapped the two arguments, and now I'm calling with 3 and 4.3. What happens is that 3 can pass through here and can be substituted for the conversion has to happen here, here, and here. So here this is an error because it doesn't know which one to pick again. This goes to number 3. This goes number 3 again because it has to convert. It doesn't convert the float to integer. Again, between template substitution and conversion, it chooses template substitution. So here again is that what is the best thing I can do? If I can just pass the type in, I can instantiate my function with the type. It's better than converting a type. So if I have to convert is a dangerous operation. I mean, it's dangerous in the sense that it might change the value. It changes the value, the presentation, the precision, and what's on. And so it's better to just pass it through. So if there's a template, it will pick the template. Otherwise, and then only later on it will pass to the type conversion. And yeah, there's usual stuff. And then float to float. This is an error again because the second one will be passed through here. You have to convert the first one, and you have to convert. You can pass the first one and convert the second one. So here is like a case in which these two guys, you have to pass one and convert one. And it doesn't matter, it matters basically how many you have to do. Since it's the same number, you don't know which one to pick, and you get the compiler error. But compiler error are good, are your friends, right? At least you know the code is wrong. You don't know why it's wrong, but at least you don't run it and get weird results out of it. C++ 11 allows you to use auto and decltype. Important to note is that C++ is a strong typed language. Every symbol has a type. Every symbol that you define has a type. So even if you use auto, so basically say deduce the type of this thing, just it has a type, all right? You don't know what the type is. You might not know what the type is when you write the code, but it will have a type, and it's just one type. So when I do auto x equal f dot value, right? Taking whatever f dot value is, I don't know, is it just a member function of f that returns something? It will instantiate the value of a variable x of that type. Then I can return auto foo, so I can return x. And even though I don't know what x is, this is just a code that will be instantiated for every type t that I'm going to use it with. X will have a type, right? So auto is used to really shorten many codes that otherwise will become extremely tedious to write. There is, for instance, a tuple. You can define a tuple in C++ 11, which takes basically a sequence of values of different types. You have a tuple of int, float, and char, and string, and you can instantiate it with 42, 3.14, z, and string hello. Right? But you see, there's a lot to type, and many times this typing can be very, very, very complicated, as we will see. So instead, you can say auto d2 make a tuple. This is a functionality that you have in C++ 11. You pass the types here. The types will be deduced, and you will get exactly the same result. So T1 will be exactly the same type of T2, but you typed much less. And this have the auto. Auto will be used a lot in many cases. So in the past, to do something like this, you should have to do like a type name t column value type, because you want to know what the type of a value is if t has this thing. Otherwise, you cannot do anything. it was impossible for you to deduce the type of this thing without using some super weird exoteric stuff. For instance, sometimes the compilers allow you to do that in the past. But you have the type T to export this value type and then assign it and then return the value. And actually, you should write T : value type here too. But by using auto, you just get this thing automatically working for you. Even there are cases in which things can get complicated, but usually the auto keyword is really very useful.
I don't get this syntax of type name where you have T value type X equal F value. I mean, usually I've seen that type name, like you want to define like a shorter name for a big type, right?
That's a type def, maybe. So, so in C++, classes and structs have different type names, right? Can have type members. We will see example of this. It's basically the class T will have a type def inside that define value type as, I don't know, int, whatever. And then you can take the class T, column value type will be identical to int in this case. And now you have to specify type name here. Because, you have to tell it is the type name. By default, the compiler assumes that when you do T : you get a value, like a static value, something. But so if you want that to be a type name, you need to specify type name. This is not a big deal because the compiler will tell you an error message saying, maybe you meant to write type name here, and then you go there and type it. But it is, it's basically accessing the type member of that class.
Just to mention that it's better to use an alias rather than to use a type definition, because with an alias you don't need the type name keyword there.
Well, you need the type name when you define the alias, though.
So you using the type name here because T itself is a template parameter. So it is not known.
It is a dependent name.
It's only known that it's a type. And about the value type, it is not known. Is it type of value? It's yes, and compiler by default assumes that value that in this unknown context the value type is a value, and the only way to point to compiler that it's actually a class is to use type name keyword.
Yes, by default, the compiler will tell you, okay, T : value type is just a value, is an integer or something, right? Yeah. We need to mute the microphone. We should just say batteries. Decltype is the opposite of auto. Right now you have auto, instantiate a variable, and now you say, what is the type of this guy? Maybe I need to know the type. So decltype does the reverse. So decltype of 10 is int. Decltype of x, when x is an int, is still an int. Decltype of x plus 10, int. Right? Because the expression x plus 10 is an integer because x is an int, is the same x as before. Yeah, okay. Decltype of parentheses x, that's tricky, is an int ref. Yeah, well, that's... You need to accept the fact of lives. This is an expression which is evaluated and returns a reference to x. Decltype, but again, parentheses x plus 10 is still int. So, it gets into your blood system after a while. But what happens now? I have a function that takes a float and a double and returns a pointer to an integer called foo, and just return the null pointer. Now, decltype of foo.
The pointer to the function that returns a pointer to an int.
Yeah.
And that's set.
It's this. Right? It's a pointer to a function that takes a float and a double and return an integer pointer. Yeah?
Great. Does it return the type which the pointer to function, or does it return the function type?
Is the function type. So it's not the pointer to the function. It's just the type of that pointer. If I have a function pointer f to a function that takes a float and a double and return an integer pointer, then this is a function pointer to a function that takes a float and a double and returns an integer pointer. This is just to get a little bit confused. But everything in C++ has a type. So the type of this foo function is this type here, int star, because it returns int star, float double. This one is a function pointer, so it has this thing here, parentheses with a pointer, which I say this is a function pointer type. What if I do this? I have always my function exactly as before, but now I do foo, or float, and double. I'm actually calling the function with default construct with 0 constructed float and double. Yeah, it returns the return type of the function, which is pointer to int. Here we are calling the function foo with some values, foo and double. And we are going to look at what is the return type of that function. Actually, we are not calling the function. Okay? The fact that there is an implementation here doesn't make any difference, because the function is not called, the function is not instantiated, only the signature is evaluated. So you go through overload resolution, you search for which function is the best one, and you kind of pretend to call it. Basically, you do the overload resolution of foo with these arguments, like we did before with 3 and 4. You can actually put 3 and 4 there, right? It will actually work. And then you go and see what is the result of that expression, the result type. So that is the int pointer. Yeah, these are basically constructed, right? You are constructing, you're kind of default constructing this double and that float. But you're not really constructing, you're just getting the type out of it, right? It's not that you're not actually calling anything. The compiler doesn't do anything there. It just look for overloads, search which function, and pretend it's calling it and see what is the type that it gets back.
But if you put the real function call, like you said, foo 3.34.
Yeah, same thing.
It's not going to call it.
Yeah, it will take 3 and 4 and say these are integers, and look for a function that takes 2 integers, and it goes through the same steps that we saw earlier, and say, okay, I need to convert this int to a double, this into a float, and I can call this foo function. And then we'll tell you, oh, this function returned an int pointer. This works also for function pointers, same thing. But here, what happens? Now I changed my function foo into something that instead of taking a float and a double, takes a reference to a float and a reference to a double. Does it work?
In the previous example with the function pointer.
Yeah.
Can you call the f pointer to the function without any additional star? And
Yeah. Pretty sure.
No,
Sure you
I
can.
don't use.
Yeah, this code is taken from the thing. Yeah, you can.
Okay.
Yeah, you can use the function pointer as a function. You can use the function pointer to call
As
the
a
function.
normal function.
Yeah. What's interesting here is that this function pointer is actually a null pointer, right? This function is not pointing to anything. You just call it, and the signature of the function is what matters. The compiler trusts you that if you need to call it, there will be a function. But if you don't, it will be fine anyway. If you don't need to call it, if you just need the type, you just get the type. You don't need any implementation. This one is slightly tricky because when I go here and do a float constructor, the float this is called this is just a compile time value. This is just an R value reference. It's something that is constructed on the fly. It cannot be changed. It can only be passed by value or by const reference, but not by reference. There's no reference to this thing. This thing is just constructed by the compiler somewhere. It doesn't exist, right? So you cannot take the address of that guy. If you cannot take the address of that guy, this is a constant value, and you cannot pass it to a function, call it float reference and double reference. Reference means basically address at the end. So you can have a reference only of something which has an address somewhere, if you can address the thing. And so this will not work. This is a compilation error. I don't know what the error is. It's got to be pretty ugly, but I don't remember what the error is. But then you can really save the day by using something which a standard library offers you. You can say declval of int and declval of int reference. So for instance, here I changed the signature. I don't know why I did that. I have a function foo that takes an integer and an int ref. Now I can create an int ref. Basically, this is just a function. It doesn't exist. Declval is just a function declaration. It doesn't have any body. It doesn't do anything. It's just a function that returns an int ref. And it will pass the int ref as a type to this thing. So now it works. Now the overload resolution kicks in and will return int pointer.
And this is decltype is always evaluated at compile time.
Always evaluated at compile time. This is actually, so decltype is evaluated at compile time. This function is called, inside the decltype parentheses, it's called an unevaluated context, in the sense that functions are not really evaluated. You don't compute the value of the function. You just look at the signatures and get the types out. So this is declval. Declaration. It does something weird like add R value reference. We'll see R value references tomorrow. It does declare the function. You see there's no body, there's no nothing. The function does do nothing. And there is no definition of the function. Okay, quickly on the decltype auto, C++ 14 offers you another keyword, actually. This is actually a keyword, okay? It's not the composition of decltype and auto. It is somehow the composition of the two, but it's like an idiomatic sentence. Say decltype auto. And then if I have x, which is an integer, and z, which is a reference to that integer, decltype auto of y and decltype auto of w will be of different type. So decltype y will be an integer, let's say, because x is an integer, but decltype of w will be an int ref. Okay? If I put only auto w will copy the value of z into w, and w will be an integer, right? This is auto. Or you can do auto ref, and then you get the reference only. But you cannot decide between the reference or plain type. And so decltype auto allows you to distinguish between the two. And why do you want to use this? I think it's not so immediate, but I give you just the code, just the final code. I have a function that takes an array, but it's not an array. It's just array type, or whatever represents some array, an index and some predicate, and this array must have the square bracket operator. And this square bracket operator is assumed to return a reference to a value. So if I'm passing A as an array, as a C array, or even as std vector or std array, I will, when I apply the operator square bracket, I get the reference to the element pointed to that index. But now I want to use this function not with an array. I want to give something that behaves like an array, but actually is doing something completely different, even though it has the same semantics. And so I can pass this array type, can be just a class or a proxy class. So the operator square bracket doesn't return a reference to something. It returns an object that refers to something else, maybe something happening somewhere else in the parallel architecture. For instance, this is used, for instance, when you do remote method invocation on an object living somewhere else, and you get something here which is not a reference to that object, but something that represents the object. And then here I can say decltype auto ref. Give me something that behaves like a reference, because this is what I want to do it. And it will be a reference if this is actually an array, or will be just an object if it is not. Sorry, you have a question? No. No, you don't have a question, right? No, it just raises his hand.
I have a remark here. So in this your example, whereas with the decltype auto usage, can you go? Yes, you can substitute here decltype auto with two ampersands with the same with the same effect.
The universal reference.
Yes,
yeah.
And there are cases where you cannot. If you return something, then it's particularly useful.
Okay. Yeah. These things anyway pops up usually when you are writing generic code. So a code that doesn't know what this thing is, or doesn't know how, you don't know exactly what will be passed to you, but you assume that they behave in a certain way. And so you will basically end up writing something like this. And when you write generic code, this is actually quite useful. And I think we are over time, so we can, I guess, time for a break. We come back at 3:30.